All right. So this is a paper on privacy that I wrote with Arpita Ghosh at Cornell. And this is actually my first foray into publishing in the privacy realm, but I have had for many years the status of an enthusiastic fan watching from the sidelines as this amazing field grew from its infancy into the quite mature state that it's in today. And I imagine many of you felt the same sort of excitement that I did last summer when differential privacy experienced a sort of coming-of-age moment as Apple announced that they're incorporating it as part of the software stack in the next iPhone OS. And as a theoretician, I'm proud, first of all, that our subfield was able to contribute such a useful technology. I'm pleased that Apple is taking such a principled approach to data privacy. And I'm especially excited as a theoretician that in a presentation where they were only able to devote 3 bullet points to what's cool about differential privacy, the second of those 3 bullet points was strong mathematical guarantees. And this was not an academic presentation either. This was a trade show. So apparently people really care about differential privacy, and they even care about its strong mathematical guarantees. Let's take a moment to look at what those mathematical guarantees are. So Cynthia Dwork has a wonderfully precise yet plain English formulation of what is guaranteed by differential privacy. It ensures that the ability of an adversary to inflict harm should be essentially the same, independent of whether any individual opts into or opts out of the data set. Now let's compare that formulation of the guarantee with Wired magazine's summary of what differential privacy is going to provide to iPhone users. Differential privacy lets you gain insights from large data sets, but with a mathematical proof that no one can learn about a single individual. Did you spot the difference? Cynthia was careful to say that an individual's decision to opt in or out of the data set has essentially no effect on an adversary's ability to inflict harm. It doesn't mean that the adversary will be unable to inflict harm, just that the ability is unaffected by the individual decision to opt in or out. And that's been simplified to no one can learn about a single individual in the popular phrasing of this guarantee. OK, so I'm going to summarize these 2 types of privacy guarantees. The first one is differential privacy, a well-known concept. The second one goes by different names in the literature, and I'm going to call it inferential privacy because, first of all, it rhymes with differential privacy, and second of all, it's about the inferences that an adversary can make about an individual. And the founders of differential privacy certainly knew about this privacy notion, considered it, and deliberately avoided using it as the foundation for privacy, because in many cases it's not a desirable property. If, for example, you have done a medical study that proves that smoking causes cancer, and you want to release the results of that study in a privacy-preserving manner, you should be allowed to announce the finding of your study, even though it means that people who read that information and know that their cousin is a smoker will revise their beliefs about the cousin's probability of getting cancer. Or in Alessandro's example, if you know that blue-eyed people are evil and you know that your cousin has blue eyes, that causes you to revise your beliefs about the cousin being evil. So there are good reasons to adopt this more limited definition of privacy rather than this more all-encompassing one. On the other hand, there are certainly use cases, especially in the kind of consumer electronics world that Apple plays in, where you might want privacy properties more like this one. For example, if Apple decides to use differentially private location-based services, my graduate admissions chair, Joe Halpern, who knows that my reviews of 94 graduate applications are due tomorrow, and has received promises from me that although I'm at a theory conference with very many interesting colleagues, my top priority is getting those reviews done, might be interested in asking differentially private Siri how many of Bobby's co-authors went out to bars in Berkeley last night, and getting back the answer, 90% of them, but I've added noise to this answer amounting to approximately 10%. He would have received a differentially private piece of information that might cause quite a significant belief revision about whether Bobby is taking his duty to review grad applications seriously. And he would receive this information whether or not I opted in or out of the data set. The trouble was that all my co-authors turned on location services on their phones, and Joe thereby found out that 90% of my co-authors were spending last night in bars. So in this circumstance, Apple fulfilled its obligation of differential privacy, but might be construed to have violated the implied assumption that no adversary observing the outcome of the data analysis learned anything about any single individual. So since people are going to go and use differentially private algorithms in settings where inferential privacy might sometimes be expected, it's a good time to ask the question, if you run a differentially private mechanism, when does it imply that you get inferential privacy? That's the question that our paper seeks out to answer. And I'm trying to summarize the paper in one slide. So for now, I will just say the answer is it depends on subtle properties of the adversary's prior. And you could summarize these subtle properties by saying that if no individual's data correlates very strongly with many other individuals, then differential privacy implies inferential privacy. And otherwise, in general, it does not. And a running theme in the paper is that the most useful quantitative tools for identifying this property and deriving quantitative guarantees from it come from statistical physics, and in particular, the type of techniques that are used to analyze magnetism. So now, with that, I'll go into the technical part of the talk. You probably have seen the definition of differential privacy before, but if you haven't, it simply says that you have a randomized algorithm M that takes as input an n tuple, x or y. And if you give it two inputs that differ only in their ith coordinate, then the probability distributions that the mechanism outputs on those two inputs should differ multiplicatively by at most e to the epsilon. OK. If we were to take the plain English definition of inferential privacy from a couple of slides ago and try to formalize it, on a first attempt, we would get something like this. The posterior probability that individual i's data value is z cannot exceed the prior probability by more than some small factor, which I'll denote by e to the nu rather than e to the epsilon to distinguish these two privacy parameters from each other. There's a problem with this definition, which is we're talking about prior probabilities and posterior probabilities, but we never said where those probabilities came from. So inferential privacy rather than differential is a property not only of the algorithm that you run, but of the prior distribution that the adversary has before observing the algorithm's output. So the second try definition just introduces a set of prior beliefs into the scope of the definition and says inferential privacy is a property that an algorithm has with respect to a set of priors if this inequality holds whenever the prior distribution encoded on this right-hand side belongs to the set delta. And the actual definition that we'll use is basically this one, except I did something weird. And instead of taking one value z that an individual's data might have, I consider two possible values, z0 and z1, and I look at the probability ratio in the prior distribution and the posterior distribution, and I ask that that ratio should not go up by a factor more than e to the nu. This definition differs from the previous one by at most a factor of 2 because I'm just taking a ratio of two quantities, each of which in the previous definition was bounded by e to the plus or minus nu. And the reason I'm setting it up this way is because a short little calculation with Bayes' law lets me rewrite it in this convenient form. That the probability of outputting a given O, given that individual i's data value is z naught, is not very different from the probability of outputting O, given that it is equal to z1. And that's a very convenient form for working with the definition of inferential privacy. For example, it lets you quickly derive that if the adversary's prior distribution is a product distribution, if he believes that people's data values are independent random variables, then an epsilon differentially private mechanism is also epsilon inferentially private. And the reason is simply I take this inequality defining differential privacy. I substitute all possible pairs x and y where they differ only in having z0 and z1 in their ith coordinate. And then I average with respect to the leftover distribution of the other people's data values. The fact that this distribution of x sub minus I does not depend on whether I takes the value z0 or z1 is where I'm using the assumption that the prior is a product distribution. And so the averaging works only because I'm assuming that I's data value is independent of everyone else's. A second remark is that if you don't assume a product distribution, the best that you can say in general is that epsilon differential privacy implies n times epsilon inferential privacy. So as the number of individuals grows large, inferential privacy goes out the window. And in fact, if you require of a mechanism that it satisfy new inferential privacy with respect to all prior distributions, and you want nu to be something small, it essentially constrains your mechanism to output a meaningless random value whose distribution hardly varies as the input data varies. So this just recovers the fact that was known to Dwork and many other early authors on differential privacy, that if you want the output of a randomized algorithm to be information theoretically useful for doing anything, inferential privacy with respect to all prior distributions is too much to ask for. So instead, we ask what types of prior distributions allow for meaningful and non-trivial inferential privacy guarantees. The sharpest results we have pertain to a set of distributions having a property called positive affiliation, which simply says that if I fix any n-2 bits of the, so it's a property of binary strings, not of n tuples over some arbitrary alphabet. It says if I fix n-2 of the bits and look at the marginal distribution of the remaining 2, they are non-negatively correlated. And this property is satisfied. That's equivalent to saying that the log probability is a supermodular function, if you prefer that formulation of the definition. And this is satisfied in the most common models of heredity, disease contagion in biology, social contagion in sociology. So a lot of interesting prior distributions satisfy this positive affiliation property. And our first theorem is a theorem that reduces the analysis of inferential privacy on positively affiliated distributions to analyzing the privacy guarantee for one single mechanism, which happens to be the most commonly used mechanism in the literature. It's the noisy sum mechanism, which simply sums up the bits and adds Laplace noise with the appropriate scaling to that sum. So this is known to be epsilon differentially private. And our first theorem shows that if this mechanism is nu inferentially private, then every epsilon differentially private mechanism is nu inferentially private. Okay, so under positive affiliation, bounding inferential privacy reduces to bounding the inferential privacy parameter of this one particular mechanism. Our second theorem, it's really just a calculation, tells you exactly what the inferential privacy of this mechanism is. It's the maximum of two ratios, each of which has exponentially many terms in its numerator and denominator. So evaluating these ratios typically will be computationally hard, and you could ask how useful this theorem is. It's useful because of a miracle that occurs, which is that if you apply a simple rational function to these two arguments, the expression that you get is the magnetization of a spin system whose Hamiltonian is minus log of the adversary's prior in an external field of strength epsilon over 2, plus or minus epsilon over 2, corresponding to the two terms of this maximization. And so any theorems that physicists have developed about magnetization automatically give you inferential privacy bounds on positively affiliated distributions. And because this is an equivalence and not just a one-sided bound, it also means that if you want to prove novel inferential privacy bounds, you have to do physics. Proving bounds on inferential privacy is equivalent to proving bounds on magnetization. OK. So our third result is a matter of just sort of cashing a check that you get as a corollary of this connection to physics. So it's known that spin systems can undergo phase transitions where their magnetization varies sharply, almost discontinuously, as you vary the external field. And by adapting those examples over to the privacy setting, you get cases where inferential privacy, as you vary the differential privacy parameter of your mechanism, can undergo a sharp, almost discontinuous change. So that might be interesting for practitioners of differential privacy who are wondering how to set this value of epsilon. It shows that that decision, which might seem innocuous, can actually be very consequential when people are doing Bayesian inferences on correlated data. So our final result pertains to the general case when data are not binary valued, but general valued, and where we don't assume this positive affiliation property. In that case, what we're able to do is define a matrix called the influence matrix, capital gamma, whose entries are not so hard to define. So if you have a joint distribution on x1 through xn, you can, one way of looking at that distribution is that xi can be regarded as a randomized function of the remaining entries in the database. Right? For fixing the distribution of these, there's a conditional distribution of xi, and in that sense, xi is a randomized function of the other bits. So in particular, this function xi has some differential privacy parameter with respect to the jth person's data, and I call one half of that parameter gamma sub ij. Okay. We package those gammas into a matrix, and the theorem says if the row sums of that matrix are bounded by 1 minus delta, then any epsilon differentially private mechanism has inferential privacy bounded by 2 epsilon over delta. So if the row sums of the influence matrix are bounded away from 1, then inferential privacy is bounded by a constant multiple of differential privacy. And this bound is tight up to a factor of 2. In particular, as the row sums get arbitrarily close to 1, the degradation in privacy really does tend to infinity. So as you vary the influence matrix, a discontinuity happens as the row sums pass through the value 1. And this is another manifestation of the phenomenon of phase transitions in physics. Another way of looking at this theorem is remember that for product distributions, inferential privacy is equal to differential privacy. That's the special case where the influence matrix is 0. And so this result is just sort of giving some quantitative heft to the notion that if the distribution is close to a product distribution, then inferential privacy should be not too far from differential privacy. So in particular, it degrades gracefully as one introduces weak correlations. But as I said, when the correlations become strong enough that the row sums of this matrix become equal to 1, it suddenly jumps up to infinity. So the graceful degradation only happens up to a certain point, which is a result that you might not have anticipated before. And those of you who know a little bit of statistical physics might recognize this influence matrix as being similar to, and the conclusion of this theorem as looking similar to, de-Bruchin's uniqueness condition. And in fact, our theorem can be interpreted as a kind of multiplicative approximation analog to the de-Bruchin comparison theorem, which defines an additive influence matrix and extracts a conclusion about the total variation distance between two measures rather than our conclusion, which is about the multiplicative I-infinity divergence between them. So in some sense, our theorem is a multiplicative counterpart to the de-Bruchin comparison theorem. OK, so that's all I wanted to tell you about the paper. I hope that you found this an enticing inducement to read a little bit more about this connection between privacy and physics. I think there are a lot of appealing directions for extending this work. An obvious one is to try extending our positive affiliation results to data that are not binary valued. And there, I think the main sticking point is one needs a natural candidate for the analog of this noisy sum mechanism, which universally has the worst case privacy guarantee. all of our results were for the setting of pure epsilon differential privacy. We didn't give any results on epsilon delta privacy, and from a practical standpoint, that's a real shortcoming of our paper. From a theory standpoint, incorporating epsilon delta privacy might, in fact, in all likelihood does break the tight connection between these questions and statistical mechanics, which might make it much tougher to get one's hands on theorems that give some quantitative bounds. There's also the interesting question of exploring trade-offs between utility and inferential privacy, which I sidestepped in my paper by not even introducing a utility objective into the discussion. And I also think it's interesting, just from a network analysis standpoint, to ask, are there certain individuals who, due to their position in the social network, are more susceptible to privacy violations than others because their data correlates more strongly with other people's data? And how does that notion of network centrality relate to other ones like eigenvector centrality? Those are just some concluding thoughts on the paper. I'd be happy to take a couple questions. Yes.
So for the positive affiliation result, the one that is the noisy sum result, so is there like a nice relationship between nu and epsilon?
It depends whether you think that formula with exponentially many terms in the numerator and denominator amounts to a nice relation. So there's the nice thing is there's an explicit formula you can write down, and it only occupies about that much space on a slide. The trouble is that it occupies exponential time to actually evaluate it. But the saving grace is that there are entire books about methods for estimating exponential sums of that type.
You have some ability to compose these kind of corrections. Going from two data sets, and
Yeah.
you have a prior that seems very sensitive because you might change the prior after learning the first fact, right?
Right. So yeah, I often get that question about composition. There's a trivial answer to your question, which is that there are composition laws for differential privacy. Okay, so you could, if you run the composition of two differentially private mechanisms, you can compose their epsilons and then run our formula to get. But if you're asking whether some superior composition property happens that's better than doing that naive thing, as far as I know, the answer is no. But it's a great question.
Great, wonderful. Thank Bobby again.